Hello students, this video is for the Chapter 12 multiple choice review. You probably noticed that the Chapter 12 multiple choice is much shorter than the other chapters. There's only 11 questions, and that's because we don't really go too much in depth with the transformations to achieve linearity that happens in section 12.2. Most of the questions on the AP exam don't really deal with that. As a matter of fact, I'd be hard pressed to remember one. So here we're just going to be talking about inference on linear regression. Let's jump right in. For exercises 1 through 6, they give you this output. And remember, this computer output, sometimes they refer to as Minitab. Sometimes they give you output that they call Fathom output. Sometimes they call it, R output or something like that. But in every single case, we're just talking about output in terms of, from the computer. So there's a lot of pieces of information here, but let's try to answer these questions, and that'll motivate our discussion of the output. The equation of the least squares regression line, remember a least squares regression line in statistics, is the one that is y hat is equal to a plus bx, where the y hat represents a predicted value for the response variable, and that x represents the actual value for the explanatory variable. And when you fill in this in the calculator, remember you're doing stat calc linreg a plus bx. They wrote it out as price and appraised value, but we know that price is, in this case, the response variable, and appraised value is the explanatory variable. So it's basically asking which one of these is a correct LSR line with the values that are taken from the computer output. Looking at the computer output, we can find the slope very easily. The slope is a coefficient, but it's not a constant coefficient. It's the coefficient of appraisal. In other words, we're going to take the appraisal value, which is the explanatory variable, and multiply it by a certain number, the coefficient of the appraisal value, so that we can add it into our linear regression line. So this number, the coefficient of appraisal, in other words, is the coefficient of x, the coefficient of the explanatory variable. So that's my slope. So now I'm going to go through and delete all the ones that don't have that as their slope. This is the wrong slope. This is the wrong slope. And this is the wrong slope. Now we only have a choice between B and C, and we need to identify which one is the y-intercept. Well, looking back at the computer output, the constant coefficient, that 127.27, that's of course going to be our y-intercept, the constant coefficient. So 127.27 is our y-intercept, that's going to be this one. Now keep in mind, usually in algebra you dealt with like y equals mx plus b. In this case, the constant term, the y-intercept, comes first, and the slope comes second, y equals a plus bx. All right, that's question number 1. Number 2 asks, what is the correlation between selling price and appraised value? And of course, correlation here, that word correlation, indicates that we're looking for the value of R, the Pearson correlation coefficient. And that value can be gotten easily from the calculator by doing this same procedure, this stat calc linreg, and beforehand turning diagnostics on. That is, of course, if you were doing this in the calculator yourself. However, they've already given us this computer output. I'm looking through this whole entire output and I don't see anything that says R. However, I do see something that says R squared. I'm looking at R squared right here. That's 86.1. That R squared value is not the correlation coefficient. We call it the coefficient of determination. R squared is the coefficient of determination. It tells us something slightly different. In any event, this value right here, this R squared, we call it the coefficient of determination, which in other words is R squared. Well, if I'm looking for R, I need to take R squared and square root it. 86.1% translates to 0.861. So if we come back down here, 0.861 is the R squared value. Let's calculate the value of R. And since 0.861 is R squared, we can put it to the 0.5 power or square root it. Either way, you're going to get the same value, 0.92, let's say 8. And they rounded it to that. Before we give a solid answer for this, there are positive and negative values for that R. So we need to figure out whether this R value is supposed to be positive or negative. We look for the slope. And if the slope is positive, then the correlation is positive. If the slope happened to be negative, then the correlation would be negative. You'd be going down. But don't worry, in this case it's positive. So, well, I mean, you shouldn't worry either way. Worrying is going to cause ulcers. But anyway, your value should be 0.928 positive value because it's not negative. My slope is positive. Moving on to question 3, the slope beta of the population regression line. Notice we're talking about a population regression line. We're not talking about the sample regression line. So we'll go through and make sure none of these are talking about the sample, and it turns out this is talking about a sample of 16 units. We're not talking about that. We're talking about in a population of units. Everything else talks about population, population, population. This one talks about an exact increase of an individual unit. First of all, in statistics, we never want to hang our hat on something that's exact. Most of the time we try to use weasel words like approximately or roughly or average. Individual unit, that's not what we're talking about either, so let's cut that one off right away. B, C, and D are our possible answers. And notice that D talks about when a unit's appraised value is 0. In other words, when X is equal to 0. That sounds to me like I'm identifying the y-intercept, not the slope. So I can cut that one off as well. Now it's a choice between B and C. And remember, slope's definition in a population regression line is the average increase or change in Y based on a change in X. So we're looking for the correct answer, which is talking about change in Y when X changes by a certain amount. This 1,000 is usually 1 in problems like this. The only reason we have 1,000 here is because the X value goes by thousands of dollars. So we're trying to figure out which one says change in Y when X changes. Okay? So in this case, price is our Y value and appraised value is our X value. So we're looking for price being first, like this. The average change in Y when X changes. That's correct. Remember, we're looking for the average change in the response variable when the explanatory variable changes. That's what slope is, the change in a Y response variable when the explanatory variable changes. All right, that was question 3. For question 4, is there significant evidence that selling price increases as appraised value increases? To answer this question, test the hypotheses. Well, let's look at the hypotheses and figure out which ones are bogus. Beta equals 0, beta equals 0, beta equals 0. Those are all good for H null. Beta equals 1, we usually don't do that, especially when we're talking about slopes. Slopes are talking about, is there a relationship or is there not a relationship, right? So we're not trying to figure out whether beta is equal to 1. We're not looking for a specific relationship. We're just looking for whether there's a relationship in the first place. Beta is greater than 0. We never have greater than in our H null, so that's no good. The only thing that we have now is to figure out if it's a one-tailed or a two-tailed test and which direction. Well, it says selling price increases as appraised value increases. That seems to be a direct relationship as Y increases, X increases. So we're looking for positive slope. In other words, beta is greater than 0. Beta is greater than 0. This is our guy. Moving on. Question number 5, still referring back to that mini-tab output. Confidence intervals and tests for these data use the T distribution. With degrees of freedom, well, remember that degrees of freedom for regression is the degrees of freedom is equal to n minus 2 because there are 2 variables, right? Going back to the output here, let's see, 16 condominium units. That means our n is 16. That means our degrees of freedom is 16 minus 2, or 14. Not too bad. 95% confidence interval for the population slope beta is, well, first we have to start any confidence interval with thinking about what confidence intervals mean. Remember that it's a point estimate plus or minus the critical value times the standard deviation of the statistic. And remember, in this case, the point estimate is just going to be B. That's the sample slope. We're estimating the population slope. So B, in our case, is 1.0466. Oh man, I can't use that to fool this problem because all of these point estimates are 1.0466. Okay, in order to find that 95% confidence interval, we're going to use, let me use another highlighting for that. Let's use yellow. In order to find that 95% confidence interval critical value, we're looking for a T value because with regression inference, we always use T. So let's draw our curve. So here's our T distribution. It's a flattened distribution, and it has 95% of the data between these 2 sticks. We need to figure out what percentage of the data lies outside of the 2 sticks and the tails, and then to figure out what the value of this stick is. That's going to be our critical value. So since there is 2.5% of the area to the left of this tail, that means our critical value that we're looking for a 95% confidence interval is going to be this value. We figured out this value using the inverse T function, inputting the amount of area to the left of the stick, and also the degrees of freedom, which we found out before was 14. So we know that this is our function. Let's go to second distribution. Let's go down to inverse T. We're putting in 0.025 and 14 is going to be our degrees of freedom, not 16 as I previously had put in for another problem. Here's our critical value, which is 2.14479, rounding 5 for 5. 2.14479. So the last part of our calculation that we need is the standard deviation of the statistic, in other words, the standard error. We have to go back to that Minitab output to look for that standard error. Looking back here, we always find that standard error in the same place. The standard error coefficient, not of the constant, but of the appraisal, because the appraisal, that's that response variable that we are using. Oh, I'm sorry, the explanatory variable that we're using. The constant standard error coefficient is not something that we use in AP statistics. So 0.1126. Moving back here, 0.1126 goes there. And notice that I'm not going to go through the trouble of filling this in because all of these say 1.0466. What I'm really just trying to find here is the plus or minus part, or the margin of error, which turns out to be approximately 0.2415. Looks like we have our answer. All of these other margins of error are not correct. Looks like this margin of error was probably generated with a z value, a z critical value. You just got to be careful that we're using t whenever we deal with regression inference. Moving on to question 7. Which of the following is not one of the conditions that must be satisfied in order to perform inference about the slope of a least squares regression line? Well, you should remember that there is an acronym that we use for remembering those conditions, and that acronym is linear. Let's go through one at a time. Linear, that L stands for the fact that the grouping of the data, the form of the data, is in a straight line. That I stands for independent observations. We want all of the observations to be independent of each other. That N stands for normally distributed. For each value of X, the population of Y values is normally distributed. Oh, that's this. So that is correct. We're looking for is not one of the conditions that must be satisfied. We're going to come back to that must in a second. So there's our N. E is equal standard deviations. We want the standard deviations to be equal across the different Y values. I'm sorry, the different X values. Yeah, and this is that. The standard deviation of the population of Y values should be the same. Let's see. A stands for and then R is random. It comes from a random sample. Okay, so the straightforward ones are gone. Now we're left with the things that are not so straightforward. The sample size has to exceed 30, and there exists a straight line, y equals alpha plus beta x. This is the population regression line. So for each value of x, the mean y value of the corresponding population of y values lies on that straight line. Well, this classic example is the exact same example that you saw at the beginning of the video from this. For all of these distributions of x values, there is one value that exists. I'm sorry, for all these distributions, I should say, of y values for each x, there exists one mean y value through which that line passes. That's that mean of y's. So this is literally described in the textbook, so you could probably guess this is not the correct answer. The last one might surprise you. This does seem like it satisfies one of the conditions, right? It seems like it satisfies the normal condition. However, remember, it says it's not one of the conditions that must be satisfied, right? If the sample size is not greater than 30, we can still do linear regression inference. We would have to figure out another way to satisfy that normal condition, but we don't have to have over 30 samples. As a matter of fact, we did a couple of examples in our chapter that had a sample size of like 10 or 12. We just did one about the sample size 16, right? Degrees of freedom 14 means sample size 16. We were still able to do regression inference, even though the sample size was less than 30. So this one is one way to satisfy that normal condition, but not the only way. All right, moving on to exercises 8 through 11. Here's another piece of computer output. And notice here they refer to statistical software, whatever that software happens to be. And sometimes it looks a little bit different, but it looks like this looks very similar to what we had before. The correlation, correlation, we know what that is. Correlation is the value of R. So we're looking at R squared, which is 8.1%, and we're trying to translate that into an R. And 0.081 to the half power is 0.28460. So looking for that here, 0.285, 0.285, positive and negative. Now we have to take a look at the slope. The coefficient of average putts is a negative value, so that means our correlation should be a negative value as well. Here's our correct answer, 8 is A. Moving on to question 9, suppose that researchers test the hypotheses H null and we know H null is going to be beta is equal to 0. HA is beta is less than 0, okay? This makes sense to me based on the data, but remember, we try to come up with hypotheses before we look at the data, before we look at a regression. So hopefully they made this hypothesis before the regression. The value of the T statistic for this test, well, we're looking at a T statistic. And for regression, the T statistic is equal to sample slope minus the population slope divided by the standard error of the slope. So many of these things we know from the problem. That sample slope, that's going to be the coefficient of average putts. That's negative 4139198. So that is 4,139,198. It doesn't seem that serious, right? You shouldn't go into the millions here about putts for the PGA Tour. But then again, here we are. And then the capital beta should be the beta keyed into that null hypothesis. In other words, we're subtracting 0. So we don't really have to write that out. The standard error of the beta of B, I should say, is going to be that standard error coefficient of average putts, just like we did from the last problem. That's 1,698,371. Wow, that seems like a lot. So we're going to take this number divided by this number. Pretty straightforward. And we get our value of negative 2.43716. If you were doing this problem by hand or on paper or as a constructed response, I would ask you to take it for 5. In this case, they're rounding to the nearest, well, thousandth or hundredth, depending on which answer, but we're looking at negative 2.44. All right, so that correct answer is D. Moving on, the p-value for the test in question 12.5. Let's see, question 12.5. Oh no, that's not what I'm talking about. It should say not question 12.5, but question 9. Is 0.0087. Wow, that's very small. Remember what happens with a small p-value, right? We always compare the p-value to alpha. And in general, we don't have an alpha value in this particular question, but in general, alpha refers to like the level of significance of the problem. So 0.0087 is very low. In other words, we can say that the p-value is likely less than alpha. Even if we're fairly conservative and we use an alpha value of 0.01, 0.0087 is still less than that. Remember, when the p-value is less than alpha, this is straight from the first time we ever did a significance test. When p-value is less than alpha, we reject the null hypothesis. That's what that says here. All right, I put in all of the possible answers here. We're going to go through and try to find the correct one here. And in order to motivate that, I'm going to give you the definition of p-value as found on StatTrek. Remember StatTrek we worked on during the summer assignment. The p-value is the probability of observing a test statistic as extreme as our observed statistic, whatever our observed statistic happened to be, assuming the null hypothesis is true. This part that says assuming the null hypothesis is true, this is the piece that we're going to be able to use in order to answer this question. Well, what's the null hypothesis in this case? That null hypothesis is that beta is equal to 0. In other words, there's no linear relationship between average number of putts per hole and total winnings for the players on the PGA Tour World Money List. That part is replicated here in choice D. If there's no linear relationship, in other words, beta equals 0, between the average number of putts per hole, which is X, and total winnings for the players, which is Y hat, the probability of getting a random sample of 69 players, that same exact sample size, right, that yields at least a least squares regression line with a slope of this or less is 0.087. This is the straight up definition of p-value. It's the probability of observing a test statistic as extreme as our observed statistic by using the same procedure, getting a random sample of 69 players. Now, letter C says something very similar, but there's one problem with letter C. Keep in mind that letter D is talking about the p-value for the test. The test is testing a population parameter. C says if there's no linear relationship, yada, 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 for the players in the sample. Oh. So now, the players in the sample, we already know whether there's a linear relationship. That's what this is. The linear relationship is negative 4 million, blah, 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 as the slope, and 1,698,371 for the y-intercept. Ooh, I'm sorry. The y-intercept is 7,897,179. Anyway, there is a linear relationship with the sample. We know that. We're trying to figure out whether there's a linear relationship in the population. So this isn't a question if there is or is not a linear relationship. This question has already been answered. The sample we know about. We don't know about the population, the total winnings for all of the players on the PGA Tour's World Money List. Now, these first two, A and B, both talk about the probability that there is no linear relationship. We don't know the probability that there is or is not a linear relationship. We're saying if there was no linear relationship, the probability of getting this or something more strange is 0.0087. So both of these talk about the probability being exactly 0.0087. This one we cut out because we're only talking about 69 players, the sample. This one we cut out because even though it's talking about population, this isn't really what the p-value's job is. The p-value's job is the probability of observing that, assuming the null hypothesis is true. So we have to start with that assumption. And then last but not least, this says the probability of making a type 2 error is 0.0087. So be careful. You know that the probability of making a type 2 error, that is based on accepting a null hypothesis that is false. And maybe they're throwing this into this question because you know that the probability of making a type 2 error is symbolized by, you guessed it, beta. This beta talks about type 2 error. This beta up here, wherever we're at here, this beta up here is referring to the population slope. So it's the wrong beta. Nice try. The only one left is choice D. Moving on to question number 11. A 95% confidence interval for the slope beta of the population regression line is, well, here we go. We start out with the point estimate and then add and subtract the margin of error, which means we go back to our computer printout and figure out what the point estimate was, what the crit value is, and what the standard deviation of the statistic is. And I'm pulling that in here for reference. Okay, we're starting off for what the slope is for the population. In order to figure that out, first we talk about the point estimate, which is the slope of the sample, which in this case is the coefficient of average putts. There's my negative 4,139,198. So that's going to go there. Using that, I can cut off two of them right away because they're starting with the wrong point estimate. Next, I have to figure out what the critical value is in the standard deviation of the statistic. Well, I know the standard deviation of the statistic is going to be right here. That standard error coefficient of average putts. That's 1,698,371. We can be relatively sure that the critical value isn't just going to be 1. So we can say that this is probably not the right answer either. So we can cut this one off. So now we're stuck between 2. And you can see that they're very close to each other, which means one of them is using Z and one of them is using T. But remember, we're going to be using T. So the T critical value for a 95% confidence interval is calculated in this way. We draw the T distribution, 95% in the middle, 2.5% in each tail. I know that 2.5% is 0.025, and my degrees of freedom from a random sample of 69 is 67. So I plug this into the calculator, I get negative 1.99601. So now using this information, I'll take these two numbers, multiply them together to find my margin of error, which is 3,389,965.5. That looks pretty similar to choice E. As a matter of fact, it's much closer to choice E than it is to choice D. And you can see if the person took 1.99601 and rounded it to even the tenths or even the hundredths place, they would have gotten 2. So multiplying 2 by the standard error gives you the exact number that they got. So they rounded in the middle of the problem. Shame on them. If you come up to a problem like this on the AP exam and it's not exactly correct, you're looking for the one that's closest because there are a lot of different rounding rules that people could follow. And it's definitely not 3,328,000. 3,396,000 is really, really close to 3,389,000. So that's what we're looking for. All right, so the answer is choice E. All right, that was the video on the multiple choice review for chapter 12. We talked about regression inference, and we learned a little bit about ourselves. Good luck studying.